Hello, welcome to my DConf 2020 online presentation. This presentation is about trusted code in D, an exploration of trusted code in D. And if you look at the bottom link here, you will see that I have a GitHub repository where you can look at the code and follow along if you wish. All the code that I'm going to show in here is going to be in there. All right, so let's talk about memory safety, because in order to talk about trusted code, you have to talk about memory safety. So there are real problems with memory safety in real applications. So if you look here, Chrome, 70% of vulnerabilities caused by memory issues. Developers using C and C++, full control over how they manage an app's memory pointers, but there's no help from the language itself to determine whether a pointer is safe to access or not. Same thing with Microsoft. This is for Windows, so 70% of all security bugs in Windows are memory safety issues. Once again, C and C++, memory unsafe programming languages. So it's becoming very, very important for a programming language to address memory safety issues and make sure that these issues are either caught by the language, prevented by the language, or they make it easy to catch them or prevent them. So what does memory safe mean? In 2017, Walter had an interesting statement. I believe memory safety will kill C. And Scott Meyer's response was, wow. And he's right, because C is one of the most prevalent languages in the world. I mean, it's probably the most popular language, even for new projects. And to say that, memory safety is going to kill C is a pretty bold statement. But we are in this world where we have Rust and we have D, and we have languages that promote memory safety. So let's talk a little bit about memory safety. I'm not going to go over everything that, Walter's whole presentation, but memory safety violations consist of accessing memory you should not have access to, like buffer overflows. Treating memory that is a scalar type as a pointer type. So this is an important one. You have, let's say, an integer, like the dead beef example, right? You have an integer and you recast it as a pointer. Now you can access whatever piece of memory that integer really would be pointing to. And dangling pointers. So a dangling pointer is a pointer used after it's no longer allocated to the thing it was originally allocated to. So you allocate one object, you free that object, but you still retain a dangling pointer to that object. Now you reallocate that memory to a different object. Now you can access the memory of that new object through the old pointer, and you have lots of problems. And really, this is kind of like interrelated, all these problems, right? So let's talk about D's safe implementation. A safe function cannot do pointer math or indexing. So if you have a pointer, you can't add a value to the pointer and have it point to something else, or you subtract a value, have it point to something before it. And you can't do indexing, so you can't say, look, give me the fifth element in this array. C is different, it allows that, no problem. That is a C array. A C array is a pointer. But in D, we have an actual array type that has bounds, so you can't do, for pointers, you can't do indexing, but for arrays you can. For actual arrays, though, we don't allow you to access arrays out of bounds. So if you try to access elements that are beyond the length of the array, or somehow before the array, you can't do that. The compiler is going to prevent this. The compiler is not going to prevent this, but the runtime does. So as long as you, and especially in safe code, it is enforced. I think at this point you cannot turn it off, but maybe you can. I'm not sure. You cannot use scalar data reinterpreted as a pointer. So again, casting dead beef to a pointer, you can't do that. Or using a union, right? You can't change mutability type constructors. So going from immutable to mutable is not allowed in safe. And also you cannot access G-shared data. These two items really have to do with threads. So if you have a thread that has access to an immutable piece of data, you cast it to mutable, that mutable piece of data could have been shared with some other thread, and now this other thread is looking at it as an immutable and you're changing it, so we're causing undefined behavior and all kinds of problems. You could read like a shared pointer. You could read a shared pointer or gshared pointer, and it's partially written by one thread. So now you have access to data you shouldn't have access to. You cannot take the address of a local variable, or a ref return. So you can't take the address of these things. The idea is we don't want to allow you to return access to data that's going to go away. Like, let's say it's on the stack or it's in some other piece of memory that's going to go away. We don't want you to have access to that. You can't declare uninitialized pointers. So there's the ability to declare types with equals void, which means, don't initialize this. We obviously don't want to allow that for pointers, because that would mean that you just have access to whatever you want or whatever that garbage was pointing at. And you cannot call system functions. So this is a pretty obvious thing. If you have a system function, so for those who don't know, there are safe functions and there are system functions. System functions basically allow you to do everything you want. There's no stopping you from doing anything you want. Safe functions cannot do that. So the problem is that unsafety is sexy, right? More interesting things are not safe than are safe, right? The most interesting part of programming, I/O, interacting with the user. If we didn't have the ability to interact with the user, if we just crunched numbers and never showed the answer to the user, what is the point of having the computer, right? If we never use networking, what's the point? So I/O is inherently unsafe because you're passing around, you're calling into the operating system, right? And the operating system is unsafe. A hello world program cannot be fully safe. It must use system calls to print to the screen, right? You don't want to be this bubble wrap guy. You want to be the roof guy. We all want to be dangerous rebels. It's in our code, right? We want to do some crazy fun stuff that has nothing to do with just adding two numbers together or multiplying numbers together, right? That's not that interesting. But there is an awful lot of safe code that you do have to do. And that code we don't want to have to worry about, right? So we get to this part of the presentation I call Trust Me, because now we're going to introduce the trusted function. Trusted functions bridge the gap between safe code and system code. Let's take an example, the POSIX write function. So this is the operating system function, system call, that is used to write data to a file descriptor, file, network, whatever it is. Okay, it is not safe. And the reason it's not safe is because you can see here we're giving it a pointer, and we're giving it a number of bytes that I want you to write from that pointer on. Now, the file descriptor is safe. That's fine. If you're passing an invalid file descriptor, you'll get an error. So that's not a problem. But passing in a buffer with some number of bytes inside a safe function, we allow you to pass in whatever number you want. So this obviously can't be called from a safe function and be considered safe, because you could access any number of bytes from any position that you have a pointer to. But we can wrap it in a safety function. So safe write here calls write, but with the knowledge that the buffer it has, we only have access to the buffer and its length, and bytes that are in its length. We don't have access around that, so no problem. We can do this. And we can mark it as trusted because there's no possible way you can call this function from a safe context and have it be unsafe. So this is what you have. You have this boundary of a safe or a trusted function, and all you have to do is review the trusted function to know, okay, this can only be called in a safe way, so it must be safe, which is great. So to recap that, let me just go through what I think is the most important part of trusted. You're limiting the review of your code. Okay, trusted functions allows calling system functions, but the true benefit is to be able to limit what code needs to be checked by hand, right? You only want to have to check by hand, assuming that the safe functions obey their spec. You only want to have to check the trusted functions. if you need to check the safe functions for safety, what's the point, right? You might as well just let safe functions call trusted or system functions, right? So if trusted functions and APIs are written correctly, there should be no reason to check safe code, and we always have to do this by manually verifying the trusted functions for safety and thinking of any possible way that those trusted functions could be called from safe code in a way that violates the memory safety rules, the rules we talked about in the beginning. So let's talk about a tagged union. For those of you who don't know, a union is not safe. Remember, we talked about a union between, let's say, a pointer and a scalar cannot be made safe. But a tagged union can be made safe because a tagged union has a tag that goes along with the union. And the tag says which member of the union is valid. And we know it's valid because we set it, right? So if you have let's say a tagged union, we're going to talk about a tagged union between an integer and an integer pointer. Now, if you have a union between those two things and you've set the integer, you know the integer is valid. If you've set the integer pointer, you know the integer pointer is valid. If you set, let's say, the integer and try to get the integer pointer out, we should have an error, right? If written properly, we have tagged unions that can be considered memory safe, right? If we write it properly. However, we want the compiler to help us as much as possible. We want the compiler to check almost everything that we can possibly have it check and narrow down what we have to actually check manually to the smallest number of lines of code, right? So before we get into this, I wanted to bring your attention to this bug, 2655, which I found when I started writing the code for this presentation. And the bug says that, even though templates should infer safe or system based on usage, attribute inference accepts unsafe union access as safe. So you have basically this exact example that I'm trying to show here, and it compiles as safe even though it's not. This is a problem. I think this bug is kind of important to fix, but it's not fixed as of this recording. So what you're going to see if you go look at the code that I have listed, right, the code that I listed in that URL, you're going to see a lot of extraneous safe and system tags because I basically had to put in there what I think should have been inferred, right? And it works, right? Because I know if I tag this safe and it's not actually safe, the compiler is going to complain. So let's move on. We're going to go to our first implementation. So this is my first attempt at an implementation. I am not concentrating at all on making the code at safe, but making it safe in terms of what I feel is safe. And right here we have two values, T1 and T2. Could be any two values. We have a tag that's true or false based on which value it is, and I use enums to help me with that, so I'm not writing true and false all over the place and trying to remember what means what. So constructor, very straightforward. We set the right value and we set the tag based on that. Assignment, same thing. The only thing here is I want to make sure we destroy the original value. If there's some complex destructor that has to be run on the original value, we want to destroy it. Now, technically, I should also set the value to the init of the new value, but I'm not doing that. But I'll leave that as an exercise for the reader. Anyways, so finally we have the destructor and the get function. So the destructor destroys the correct value, the one that was set last. And the get function gets out the value that was set. Now, if you try to get out the wrong value, it's going to throw an exception, as expected. And if you get out the right value, it just returns it based on what you pass in. Okay, so we have our module tagged union, we have our tagged structure, and we have a unit test. Let's run it. We have a tagged union, we set it to an integer, we verify we can get the integer, we try to get the integer pointer, verify that it throws an exception, etc., etc. and it passes unit tests, and it's fine. Now, the question is it safe? Okay, is this function, is this struct actually safe, right? The answer is yes, it is safe. It can't result in a memory violation because we're not giving access to memory we don't own. We're not treating scalars as pointers, right? We throw an exception if you try to get it the wrong way. And there's no dangling pointers, right? We're not returning pointers to anything. We're just returning references. Now, it's important to note that we're returning references and not pointers, because in safe code, you can't take the address of a reference. So there's no way to squirrel that away. So and if you think about this, it's very similar to memory allocation, right? You allocate memory for an integer, use it, then you free it, and then allocate memory, that same memory, for an integer pointer. Okay, that's fine, as long as you don't have a reference to it as an integer anymore, right? And that's what we're enforcing. But if we attribute the unit test as safe, we're going to find that it's not, the compiler doesn't think it's safe. The compiler can't tell, right? Because the compiler doesn't realize that we have assigned this semantic value to the tag that says, oh, yeah, actually we know which value of the union is correct. So it's going to complain. It's going to change all these functions to actually system functions, infer them as system functions, and say, no, you can't call those system functions from your safe unit tests. Now, because all the function safeties are inferred, instead of seeing the actual part that makes the code unsafe, you just see this cannot call system function. Now, technically, I had to put in system tags to make it do this, but that's because of the bug. So instead, what we're going to use is explicit safe tags to further diagnose the errors. So I'm going to put in safe in here, expecting, oh no, actually I want everything to be safe. You tell me what it's actually unsafe. This is a great technique to use when you're trying to make code that's not safe to be safe. If you want to find where the inference is happening, you tag it as actually safe, and then the compiler will complain, oh, you wanted that to be safe? No, you can't do that. You can't do that in safe code. What are you doing? So I tag it as safe. We see cannot access pointers in safe code that overlap other fields multiple times. As expected, right? And that was one of the rules. You can't do that. You can't have a union between a non-pointer and a pointer and access the pointer member. But our tag tells us which one is valid. So we can mark trusted the portions of code that determine which value is valid and provide a reference to that value, right? We're going to abstract out the access to the correct value into a trusted function. So let's move on to tag union 4. And we have two new functions, access value and set tag. And both of these I've attributed as trusted. Access value gets a reference to the correct type as long as the tag is the expected tag, right? The tag says which one we've set. So as long as the expected tag is use T2, you can return a T2. If it's use T1, then you can return a T1, and that's fine. If it's not as expected, then we throw an exception. This takes the place of the exception throwing in get. As you'll see later, we're just going to use this enforcement. And the set tag. So set tag takes a new tag. If it's not the same, then we destroy the old value and we set the new tag up, right? No problem. So this is what our constructors and assign operators look like. We just set the tag to what we expect it to be and then use it. So no big deal, right? The destructor, I kind of used the fact that the set tag is destroying the current value and just set it to a different value, right? I set the tag to a different value just to use that destructor without having to create another trusted function for that. And finally, our get function becomes slightly simpler. We just, use the enforcement inside access value, and we're done. But is this safe? Now, it does compile. It does pass unit tests. However, running destructors might not be safe. and we have marked it as trusted. So one of the things to remember when you're writing a template with trusted functions in it is you want to let inference happen as much as possible, right? So you only want to trust the parts that you know should be trusted. But that's easy to fix, right? In tagged union 5, I basically removed the trusted tag from set tag, and instead of destroying the values directly, I used access value to pull the reference out and destroy those values, right? Now, are we done? How do we know that the code is safe? How do we know that everything in this doesn't need to be reviewed? All we have to do is review the trusted functions, or actually trusted function. We only have one trusted function now, right? Yeah. Here's a problem. So you can see the highlighted code right there is actually safe code. It's at safe, which means that any safe code in my file, actually, any safe code in my file needs to be reviewed. Unfortunately, because if that safe code sets the tag to a different tag, it changes the contract, right? It changes the contract, the invariant that the trusted function is expecting, and that is we only set the tag to a new tag when we assign a new value. This is a problem, okay? And there's not much we can do about it because the compiler doesn't care. It doesn't care. It says, you know, you can set a Boolean, no big deal. Why is that a problem? Or you can set an integer. The problem is that we have assigned a new semantic requirement for that Boolean. And that semantic requirement is you only set it to true or use T2 if it should be if the T2 value is set. And you only set it to false or use T1 when the T1 value was set. So how do we enforce that? How do we make it so that we don't have to review the safe code in the file? So I tried several different things. Let's try tagged union 6 was an attempt to put the tag inside the union. Now remember, you're not allowed to access a union that has a scalar value with a pointer value, right? So what did I do? I put the tag inside the union. First of all, I created these weird structures that have the tag embedded in it plus the value and did a union between those. And then also between a tag, which makes it easier to grab out, and for good measure, I threw in a poison integer pointer so that we can make good and sure that, yes, this overlaps with a pointer. And of course, we have to change our access value function so that we're accessing the val part of that structure, because now it's a structure and not the value. And finally, we leave our set tag the same to make sure, okay, we shouldn't be able to set this tag, right? We shouldn't be able to set it to tag. It's safe. However, it still compiles. Unfortunately, the compiler allows access to non-pointer union data even if it overlaps a pointer. Why is this? I think the reason is because, hey, you can do that. You know, you're not allowed to access the pointer part, so you can access the scalar part. And I find this to be a flawed reasoning. And the reason I find it to be flawed is because, well, of course you're going to want to access that pointer at some point, probably in some trusted code. The problem is now you're allowing safe code to violate the contract that the trusted code expects, or the invariant. So the trusted code can no longer be trusted. We now have to review the safe code, which is the whole point that we're trying to avoid here. For the whole idea is to avoid reviewing safe code. So let's try a different attempt. You'll notice that the URL here points at a directory because in here we have two different files. I specifically separated out this system tag into its own file to make sure encapsulation works. Remember, private is only accessible within the module, so I want it in its own module. That way you can't get around the privacy issue. Okay, so we have a system tag. It has a Boolean. Any attempts to assign to the Boolean are marked as system so that it can't be used from safe code directly. You have to use it from trusted code. But we'd still allow reading the tag because, that's fine. You can read the tag, you just can't write it. And making it, using the tag function as the alias this allows it to just drop in nicely. This is actually very similar. So this is the new tagged union code. We have to import system tag and replace my Boolean with a system tag. Now this is actually exactly the same code as tagged union 5, I believe, but I just replaced that one line. That's it. And of course, we get an error because now you cannot call opAssign from a safe function, and this is a safe function. So perfect, that's exactly what we want, right? So it passes, right? We now can call that, wrap that tag assignment in a trusted escape, which if any of you have not seen what a trusted escape looks like, this is what it looks like. We declare a lambda and call that lambda immediately. The compiler should basically inline this even when you don't pass dash inline. So essentially it's like tagging one line as a trusted call. So perfect, that's exactly what we want. But there's ways around it. The compiler allows tuple_of to bypass privacy restrictions, so you can access private data directly by using tuple_of. Now this isn't really a showstopper because tuple_of is kind of a weird thing and it's easy to grep for. So we could still possibly say, okay, you only need to search for trusted or tuple_of, but it's still it kind of leaves a bad taste. Plus, at the same time, I'm having to create this whole type that I want to act just like a Boolean, except just not be accessible from system, from safe code. It would be nice to just have the compiler do that. So that leads us to attempt 3, travel into the future when DIP 1035 has been accepted and implemented. For those of you who don't know, DIP 1035, with the URL here, is written by Dennis Corporal. I hope I say that correctly. But it allows you to tag data as only accessible to system or trusted functions. And we use the compiler to enforce those semantics. We don't have to write our own special type for it. Now the special type does kind of work for the limited test that I did, but this would be much, much easier to deal with. Plus it eliminates backdoors. It specifically calls out all the backdoors that could be thought of at the time of the writing. But you see, basically here we just tag an integer as system, and now you can't write to it from a safe function. You can't even access it from a safe function. So how would we use this? Okay, so tag union 8. This actually compiles today because attributes are ignored if they don't mean anything. So you can tag data system all day long, and it doesn't have a problem. Though technically we want it to prevent you from accessing from safe code, but we can imagine, right? We can go to imagination land and imagine that DIP 1035 is implemented, and this prevents us from running that line of assigning the tag. Probably works. This probably solves the problem. So let's talk about the 3 mitigation attempts that we had, right? To try and make it so we don't have to review safe code. And that's the point of this. We're trying to avoid having to review safe code and only make it so we review our trusted code. Attempt 1, tag inside the union, failed completely. Compiler doesn't care. I really think that should be fixed. Attempt 2, specialized system-only tags. It kind of passes, but now we just have tuple_of as another problem to look for, and possibly other issues that I haven't discovered yet. And attempt 3, DIP 1035. I believe this will pass and be a much better solution than everything we have so far. And it basically gives the compiler the control to say, oh, you want this semantic enforced? Okay, I'll do that for you. So that's basically what we're trying to do, is tell it, I have a different semantic that I want you to enforce for safe code. But are we done? Are we really, really done? No, we're not. So take a look at this program. This is a usage of our tagged union. And in this usage, we've set the tagged union to an integer. And then we call a helper function with a reference to that integer. And in that helper function, we set the value now to a pointer. The pointer points to this public value, which is adjacent to a secret value that we don't want people to know about. Now we pass both of those items into foo. And foo can manipulate the pointer by changing the integer. Right? If we run this now, we get access to the secret value. Note that everything in here is marked safe. So this is a problem, right? We don't want to allow access to a reference when it becomes invalid. So if you pull out a reference to an integer, you don't want to then provide, allow that reference to continue to exist when the data underneath has been changed to an integer pointer. Or, that's really hard to do, right? That means we have to go through and say, this reference is no longer valid. How do you do that? How do you find all those pointers and references? It's really hard to do. Or we can limit the utility of the union. I considered writing actually a version of this to demonstrate, but I think you guys can get the point. It's basically, oh, you set it to an integer, you can no longer set it to an integer pointer. Too bad. That's the end of it. But that kind of defeats the purpose of the tagged union, right? We want to kind of like a variant algebraic type, and we don't want to, there are some uses for it. There are some uses for having a thing that can only be one thing or the other and never change again. But most of the uses are, specialized. So we would like to just be able to assign reuse that memory for a different assignment. Or the final thing that I thought of was to disallow reassignment to a different type while a reference is held. Now this I think we can do, and I did try to do it, but before we talk about that, I just want to bring up a reference to Walter's ownership borrowing solution. I did read this blog article probably like 3 or 4 times, and I tried to think of a way that I could use this to help me with this problem. But I think it's really focused on pieces of memory that don't change type. So it says you have to require a const. If you want to have 2 references of the same value, you have to require a const. That could be a problem, but for sure we don't want to allow references at all. If I don't even want to allow const references to a integer as an integer pointer, right? That's not a viable solution. Maybe there's a way to enhance it, maybe like an op borrow or something that says once you've borrowed this, now it locks it as that type, and somehow you have an op return or something like that that says, okay, now the borrow has completed, but I don't know. So that's something to think about, a possibility. So let's solve the lifetime problem with reference counting. I created this struct. It goes in the tagged union module. The struct is basically just it's not a smart pointer, it's a smart reference. And the reason I say that is because I want it to have the same semantics as an actual reference. I don't want you to be able to copy this around or squirrel it away or do something with it. In fact, if there was a way I could make it so that you can't save this, you can just use it in an expression, but you can't save it. If there was a way to do that, it would be perfect. That's exactly what I want. I want this only to be an R value. Okay, so we have a counter, pointer, and a value pointer. We assign the counter pointer based on what's passed in. We increment the counter, and then we disable copying, and on destruction we decrement the counter. Simple reference counting, right? And we allow access to the value whenever you want while this reference exists in memory, while it hasn't been destroyed. Another bug, 16426, says that the compiler creates an opassign for you. If you don't define one, then it won't work. Like, you can't assign to the alias this property, which is annoying. But anyways, this works, right? In our tagged union, I add the borrower's integer, which is the reference count. So this is going to store the reference count of how many references are outstanding, right? On copy construction, I'm going to set the borrowers to 0 because this is a new piece of memory, so I don't have to worry about it, right? And finally, inside access value, now instead of returning a reference to the type, I return the borrowed reference. And in set tag, before I can change the tag, I need to enforce that the borrower is 0. Now, technically this is still in safe code. And so technically we have to make sure this stays in here. If we don't, and I'm kind of tempted to, I kind of want this to be trusted code, but it doesn't need to be. So at this point, you still have to review this line and make sure it doesn't change. But that's at least narrowing it down to that one spot. And there's a trusted tag setting in here, which I'm assuming, maybe we still keep dip 1035, so that makes sure that you can't do this in safe code anyways. And I had to add the underbar get because obviously you don't want to just destroy the smart reference, you want to destroy what it's pointing at. So that was pretty simple. There are more bugs, of course, in the compiler. If I didn't add these parentheses, it didn't work. It tried to treat those as property setters, which worked before, but for some reason doesn't work now. I don't know why. And more bugs. So here we're back to our lifetime problem. Same exact code, except I had to add these underbar gets. This is also a new bug that I filed, 213069. And if I didn't, I'm assuming that if that bug got fixed, this code would be exactly the same as before, right? Exactly the same as before. And what is the result? An error, which is exactly what we want, right? You cannot change the type when someone has a reference. Line 16, which is where it comes out of, is the line that sets it now to a pointer instead of an integer. So, conclusion. So what did we learn? I hope everyone learned that writing trusted code is not as easy as it seems. There are a lot of things to think about. And even if you think you have a safe, trusted API, imagining how the data can change underneath it is something that you really need to consider. The point of trusted is to make sure you don't have to review safe code. If you don't have to review safe code, then all you have to review is your system code, make sure that it follows the spec that it's supposed to follow, and your trusted code, and make sure that it can't allow safe violations. Dip 1035 would help. I hope that gets passed. And finally, lifetime issues. I think D has been struggling with how to solve lifetime issues for maybe 8 years. DIP 1000, the live ownership borrowing stuff. It's not helped by the fact that the compiler has bugs and that things aren't fully specified. But there is a path, I think. I think there is a path with the way that D is on to where the compiler helps enforce the semantic guarantees that we want. And that's really what I'm trying to say here is, I think we can make D the language where you only have to review certain pieces of code and you can assume that the compiler helps you everywhere else. With that, I'm going to end my talk. Hope you all enjoyed it and learned something. And I'll see you all tonight at the DConf and hopefully next year in person at the next DConf. Stay safe, everyone.